Okay, so what is image processing? Well, image processing is really the transformation of one signal into another form. But on a very practical level, what we tend to use it for is denoising or for extracting a meaningful signal from our input. Okay, so you can imagine image analysis is sort of all of the interpretation of the data. It's sort of an umbrella for everything, really, but you can think about that as sort of extracting the data from what you're doing and opening the files and all of that. But the image processing is really the processing of your signal as part of your pipeline of analysis. Okay. So, but before we go into that, I just want to recap some of the things that you probably saw during the practical and this morning. So, just a recap: your image is now comprised of data or of values. Hopefully, you all now believe me. You all saw this firsthand. You had your cursor over the image, and you were able to see the values. And this is how you would imagine a grayscale image to be composed. If you sort of squint your eyes a little bit, you can actually see the image here almost. And then we've got a binary image. So here I've represented it as 0 and 1s. This is how it is normally on a computer. But if you had a look, you'll see that in Fiji it's actually 255s and 1s. And this is just their convention. This is the type of data that they work with. They don't have anything smaller than an 8-bit representation, so they just do 0 and 255. This is Felix the cat, if you want clear. And then you hopefully all saw a composite image in the practical. So you can make a composite image from separate channels using this dialog here, image, color, merge channels. And here, so we have an image with red, green, and blue, and we separated them, and then we can recombine them with this dialog. And if we do create composite, then we create an image like this. So here I've got a little animation, and I'm changing the slider, but it appears the same each time in each position. And this is because it's a composite. So it's been designed to show each channel at the same time. So why is there a slider, you might ask? Well, this slider allows you to change the channel in which any subsequent analysis will be applied to. So for example, if you put it in the first position, then if you did find maxima, for example, it would apply it to this red channel. So you can still do some analysis on this image and just keep it in this form. Generally, if you're doing analysis, I'd say split it before you do it, just to minimize confusion. But I just want to point out to you that you can be selective with your channels in a composite representation. Okay. And here you can actually, if you open this channels tool, which is here, then you can, I say in the next slide, it's image color channels tool. And then you can actually turn on and off the channels selectively here for you to look at, right? So you might just want to see the green and the red together, so you would turn off the blue. Okay. Now, there's another way of looking at this data, which is as in color mode. And what happens here is, as you can see, we're going through the slider here, but when we've got it in the color mode, when we go in between the channels, it actually turns all the others off and just keeps that one on. And the way that we do that is, again, with this tool, this image color channels tool, and we put color here rather than composite. If I move back to the previous slide, you can see it says composite here, but here it's color. So it's only possible to have one channel on at a time. So when you click channel 1, it will just move to this first position. And also, if you move the slider, you'll see this changing as well. So these are basically two ways of handling multi-channel data. So we've got the composite mode and the color mode. And I really want to draw a comparison with RGB data. So this is this photography mode that I told you about before. It's possible to make data of this type in Fiji, of course. So one way of doing it is to merge channels, but to have the create composite unchecked. And then what you get out is an RGB image. And you see there's no slider here. So it looks the same as a composite image, but it hasn't got a slider. And if we had 5 channels or more going into this, they'd now be merged as RGB. So if we split this, we would lose data. So I just really want to highlight to you that. And you can see here it says RGB, right? And if we go back, we see it says 16-bit here because it's telling you the bit depth of the individual channels. And here it says 16-bit as well. But it's just the way that it's separated. So if you don't see 8-bit or 16-bit, if you see RGB, then you know you've created an RGB color image. And there's nothing wrong with that for certain things. But if you're doing image analysis, you probably want to steer clear of that. Okay? Keep it as a composite or in color mode. Or split the channels if you like. But don't convert it to an RGB and then split it and then try and analyze it, unless you're really sure about what you're doing. If you're really sure that you had red, green, and blue lookup tables, and there isn't any chance of any contamination, and you only had a maximum of 3 channels in your image. Clear? I know I really labour the point, but it's good to have it. And yeah, just to make the point, if you started to look at the pixel values in an RGB image, you wouldn't just have one value for each location, which you would with the other cases. You would have you would have 3 values for each pixel position, which represents the red, green, and blue component of that. Okay? But as I said, this is fine for presentations, just not for more data analysis. Okay, so that's the end of the recap. Now I want to talk a bit about mathematical functions. So I'm sure you've got some intuition for what these are. But essentially, what they do is they perform some kind of action on your input. So in our case, most often our input will be an image, and we'll apply some kind of function, and then we get an output, which is our output image. So for thresholding, the output would be a binary image, and the input would be a raw image. And this here, our function f, would represent the Utsu algorithm, or the limit that we applied, our hard limit for what's foreground and background. So functions are used very often. Almost everything you do in image analysis could be represented as a function. Some people represent humans as functions. You know, you can think of it in many ways. Inputs, food, and I won't say what the output is. Good work, you know. So start to think of things as functions, as it can help you with interpreting mathematics and things later on. But basically what we're doing in this lecture is I'm now going to take you through a number of common functions or operators which we apply for image processing. Okay. So first of all, I'm going to talk about Z projection. This is something which is very common to do during image analysis. So in this image here, which we'll hopefully play, we're just moving through a Z stack. So this was a 3D volume that we acquired slice by slice on a wide field microscope, capturing green, red, and blue fluorescence. And it has multiple slices. And what we want to do is we want to Z project it. And the reason we want to Z project it is because for the question that we're asking, we don't actually need the whole 3D stack of information. We can get away with a Z projection. So what is a Z projection? A Z projection represents the 3D stack as a single image for each channel. Okay, so we go from a 3D stack to just one image, and that image hopefully for us represents enough of that image, that raw data, to be useful for our experiment. Okay, so basically we're saying we're going to do this because we know, we've perhaps done some preliminary analysis, we know that we don't need to keep all of that information in 3D to make the measurement that will tell us about our experiment. We can compress it into one, or distill it into one image per channel, and that is good enough for our phenotypes. We can distinguish between our controls and our wild type conditions, our experimental conditions, and we can do our experiment. So we don't need to carry through our analysis those big stacks. We can save time by compressing it and make it more elegant and distilled. So how do we do that? Well, the Z projection, what it does is it moves around each pixel, X and Y pixel in the stack, and it takes the maximum pixel across Z, through Z, okay? And it just takes the maximum intensity value and then outputs that in the output image, which is just a single image. Okay, so imagine you've got your stack with multiple slices, and you're almost just looking down through the stack, and you take each pixel one by one, and you say through the Z, what is the maximum value? And we will just keep that one value and discard the rest. Okay, that's what a Z projection does. It looks through Z, and in this case we're doing a maximum intensity projection through Z, which is sometimes called MIP. So we're taking the maximum value. There are other ways of doing Z projection. We could do mean, or we could take the minimum value, or we could take the standard deviation, but typically we take the maximum value. But when you run this plugin in the practical, you'll see there's lots of different options there for doing it. And this is just a way of representing that data in a kind of compressed form. And what you get out when you Z project an image like this is you get a single image for each channel. And as you can see, hopefully it's not too light, but you can see that a lot of the detail in the image is there. So we've got a number of sort of bright clusters here, and we've got our red and blue fluorescence. So we have thrown away data by doing this, but we found for this experiment it was perfectly reasonable to do that. And then we could just use 2D analysis, which is much simpler than 3D analysis, and we were able to distinguish our conditions very effectively. So you might want to do that in your analysis. But the Z projection, this is a classic kind of image processing function that we can apply. Okay. Sure. Yes. In the normal way to apply it, you would apply it per channel, but the algorithm does that for you. So you don't have to say do it per channel. It will just give you in this case, a 3-channel output.
But it wouldn't matter if, say, it wasn't exactly the same position in that 3D.
No, the pixel, yeah, that's a good point. The pixel can actually come from different positions depending on which channel it's looking at. So that could be important. That's the sort of noise that you're introducing, and that could affect your experiment. But it's sort of up to you to interpret whether that's a risk or not, or whether it's going to do something so dramatic that it really throws the comprehending it. There would be ways around that. So for example, if you really wanted to get the same pixel in each one, then you could write a script that finds the maximum in one stack and then just make sure it takes the same one from the others. But I don't think you can do that just through the menus. I think you'd have to do that yourself. But that'd be a good challenge. That's a good one. Ooh. Okay, so I'll continue on. So image filtering is also another form of image processing, which is very common. And here are some examples of some filters. You may remember I briefly showed you earlier doing some denoising, some smoothing to our image as part of the segmentation pipeline. And here we've got an example of a smoothing filter. But also you can use these filters for example, finding edges in your image, or you can also use the filters for sharpening, which basically just retain the higher frequencies and kind of amplify them with regard to your image. So when I talk about frequencies in an image, high frequencies represent fine-grained detail, and low frequencies represent sort of undulating large features in your image. And with filters, you can actually meaningfully dissect your image in terms of frequency as well. So if you filter an image with a very heavy blur, you're extracting the low frequencies from your image. And we'll cover this a bit more later. But first I want to sort of outline to you the differences between linear and non-linear filtering. There's a sort of mathematical characterization of linear filters, which is that they are linear for addition and also scalar multiplication. Don't worry too much about what that means, but it basically means the filter is reproducible or is reversible. So if you use a linear filter, then you can always go back with a converse representation of the equation. So you don't throw away any data. It's just taking what's there, applying a transform to it, but you don't lose any information. You can go back reversibly. Whereas with a nonlinear filter, the methodology in each position could be slightly different, and so there's no way of knowing exactly how to go backwards unless you explicitly record what you did. So linear filters are sort of are the real workhorse, and then nonlinear filters are kind of specializations that do something a little bit funky, and so you can't naturally reverse them. So it's not so important that you grasp that now, but it's something that comes up a lot in sort of mathematics and image analysis, is the idea of linear transformations and nonlinear transformations. And the convolution is an example of a linear transformation, and that's what we were doing with filtering. So let's go into linear filters. So I just mentioned convolution, and this is a form of linear filter. In fact, this is the sort of archetypal linear filter. And this has equations with it, but really they're very simple. So what we do is, for example, we take our input image here, and we take a kernel. And what we want to do is, in each position of our input, we want to multiply each pixel with the corresponding one in the kernel. So if this is our kernel here, this just comprises of a 3x3 grid of ones. And what we're going to do is we're going to take each position of this kernel, multiply it by the corresponding one in the image, and go through all of them that way, sum them up, and have the output here. Okay, so in each position, we do this 3x3 dot product, and then we just put the output in one pixel in the output image. Okay, so this is it again. So we take our kernel here, the positions of our kernel, and the image, and we multiply them in each position, then we sum them up, and we put them as an output. And then we do this for each position in the image. Go on.
What is that kernel number? Why is it a 1? And is that an input that I can change?
Absolutely, absolutely. Yeah, this is a mean filter. So it's the most basic filter. You just take an array, 2D array of ones, and then what it does is it, for every pixel in the output, it's sampled all of its neighbors, and then the output just represents the average of all of those surrounding ones. So it's the most basic kind of smoothing filter that you can have. So each location has an equal weighting for that particular output. And imagine you're moving this around the whole image. So every location in your output is now an average of its surroundings from the input.
And then if I was to increase that, what's going to happen?
The power of the averaging gets more. It would get more and more smoothing. You'd have more and more smoothing effect. The problem is it's a very square filter, so you also introduce a little bit of an artifact with that if you get really big. So this is actually what's happening with the convolution. So imagine we're starting in the top hand corner, and now we're working through the kernel, our 1x1 kernel, and we're just multiplying, and you can just see me doing the multiplication there and summing it up. And then we get 1 pixel output here. So I'm just repeating the first location. And then I'm going to move to the next slide, which will show this process applied to the whole image. Hopefully. There we go. So now this is actually what you would do in a practical setting. You would apply it to the whole image, and you can just see it's running through very quickly now, what I was showing you in slow motion. And so you can see the output is a kind of blurry version of the input. It's a smooth version. You might have guessed I like making little animations. Okay. So that is a mean filter, and that's the most basic filter you can have. And here are some other filters. So a little sort of intuition for a filter is that it tends to enhance the features that it looks like. So this is quite hard to imagine with the smoothing filter, but if you have other designs of filter, then basically they try and extract signals in an image that look like the filter. So this is an example of a 1D edge filter, where we just have -1, 0, 1. So this kind of looks like this, right? It's just, it's an edge. And when you apply it to an image, it will extract the edges, which is what we've done to Felix here. And you can see that this filter has extracted the left and right edges of the image as either negative or positive based on the filter. And then if we flip it and do it in the other direction, we can see we've now extracted the upper and lower edges of the image. Okay? And then we can actually combine these. Combine.
That was my next question.
Yeah.
What if you do both?
So these are no longer. This is a 2D filter which is extracting the edges, And you can see that now we've actually extracted all the edges as either negative or positive. And then what we can do is we can either take that image that we had just previously and square it, or we could have taken the outputs of the original 1D ones. So this is part of being a linear filter, is that you can do the addition and multiplication before or after. This is the beauty of a linear filter, is that it doesn't matter what order you do it. And then, so you can either do it as we showed you in the last slide, or you do it independently and then square it, and then you get all of the edges coming out. The reason I've done this to Felix is because without any smoothing, this doesn't work very well. And because Felix is just very dramatic edges, it works well on that image. But you would find using filters just like this with no smoothing wouldn't work very well on a normal image. So just bear that in mind. And then there's second derivative filters. So this is, if you remember from from secondary school, when you were doing things like velocity, displacement, and acceleration, then you'd find that velocity is the derivative of displacement, and acceleration is the derivative of velocity. And when you look at where velocity is 0 and where acceleration is 0, you can use that to find peaks and troughs in terms of your distance and displacement. So it's the same with images. So if what we were doing before, these were first derivative filters. So we were finding where you've got where the gradient of the image becomes stationary. And with a second derivative image, we're finding where the velocity of that image is stationary. So this is actually the edge itself, dead on the edge. Okay, so don't worry about that so much, but we can basically extract that through using a filter that looks like this. So this will, similar to the last one, this will find the edges, and we call this a second derivative filter. Okay, and then I just want to show the use of these in terms of smoothing an image. So this is our input image, and we apply our mean filter, and we get an image where the larger, more consistent features have been extracted, the contrast of them has been improved. And if we were to threshold them, you can see it makes quite a difference in terms of the quality, in terms of our ability to extract these features. Okay. But as I said, the mean filter, especially if you make it large, it can start to introduce slightly square-like, it can promote square-like features in your image. And one way around that is to use a Gaussian filter. So this is a much larger filter. This isn't the image. This would be the size of the kernel that you're using on the image. But you can see it's now a very smooth graduation between the lowest and the peak intensity. So the kernel looks like this, right? And we can mathematically define it very, very nicely. And this is great for smoothing something without introducing an artifact like the square. But this won't introduce any artifacts like the mean filter can do if you use a very large one. And it's very typical. It's very typical to smooth with this filter before doing any edge filters and things like this, because it just smooths your image, and then the edges become more pronounced. And so when you apply those techniques, it's easier to see the edges as you'd want to. So you can just see here, this image had the Gaussian applied to it, and you can see that now it's really, really quite nice. The smoothing has had a very positive effect on trying to allow us to extract these features. But of course, maybe you would lose something by smoothing it, so it's not always a good thing to do, but depending on what you're trying to analyze, it can make life a lot easier. Okay, and just to make it clear, the way it works is it weights the pixels nearer the center more, so where these are brighter. So it's still taking an average of everything that's there, but it's just much more significant in the center of the kernel.
Is that problem with the terminology? Is smoothing the same as deconvolution? Or is deconvolution?
Convolution, not deconvolution,
Okay.
but convolution is the filtering. So that's the mechanism.
Okay.
So we could convolve a filter for finding edges or for smoothing the image, but the smoothing is when you apply a mean filter or a Gaussian filter, they have a smoothing effect. An edge filter on its own doesn't have a smoothing effect.
So convolution just means using a filter?
Yeah, yeah. So what we say is this process, this is the convolution, right?
Sure.
This is the convolution. Here we've got the equations for doing convolution.
Yeah.
But it's also convolution and filtering are the same.
Okay.
And actually convolution and linear filtering is the same. Okay. Deconvolution is actually the converse of convolution. So this is where you would go from what we had as an output back to our input. Okay, and in theory, this can be done just through simply doing the converse operation. But in a practical setting, you don't tend to do deconvolution this way because there's this issue where 0 pixels can cause problems in the process. So typically, if you use software like Huygens that does deconvolution sort of professionally, what it does is it tries lots of different convolutions and sort of picks the best input image that represents the output. So in theory, you don't do deconvolution in the mathematical sense because it doesn't work that well because you get problems with noise and things like that. But don't worry about that. Just think of deconvolution as being the converse of convolution, where we have a knowledge of our airy disk. So remember if we had 1 pixel or 1 point of light, what it would look like when we acquire it on the microscope, and we sort of de-smear it with that. That's kind of what deconvolution is. If you see convolution, the forward process, as being a smearing with a filter or a point spread function of a microscope, deconvolution is the kind of de-smearing of it. Okay. So now, if I haven't lost you completely, I'll talk about some nonlinear filters. So these are also useful, but they can't be represented with a nice kernel because they do a different thing depending on what they see in each location of the image. And this is kind of the difference. So with the convolution, we can define it as a nice kernel, but with nonlinear filters, we have an algorithm there. We can have a set number of steps, which is reproducible, but you can't just represent it very easily as just an image of numbers like we did previously. So for this example, I'm just representing, this is our image, say, and just an array of numbers as normal. And what we're going to do is this is going to be our median filter. And we start in this location, and then we extract the values. Okay, so 1, 1, 1, 1, 1, 2, 2, 2, 3, and we've sorted them from high to low, or even low to high in this case. And what we want to do with a median filter is we just want to take the middle value when they've been sorted. So in this case, there are 9 values, so we take the 5th value, and then this is what goes in our output here. Okay. So we just, in each location, we take the median value, and then we move to the next location and repeat it. And then you'll see that we get an output image. Joanna?
Can I ask you, with all the filters, you always have this problem that you can't deal with edges. So does it mean that anytime we apply any kind of filtering, we are losing the outer edge of our data set?
It can do, but what Sure. So Jana has insightfully spotted that these filters will have a problem with the pixels around the edge because you don't know what the neighbor is. Now, it depends what software you're using, how they'll treat that. But if you're using something like Python or MATLAB, you can choose how you deal with the edges. So you can either wrap it around. So you can say, if I'm on the edge, then I will use the values on the other side of the image to pad out my kernel. Or you can mirror. So on the edge pixels, we just mirror the pixel to the right and pretend it was to the left and around any blank pixels. Or you can just set it as 0 and carry it that way. Or you can do something which is called valid, which is you just output a smaller image than you started. And all of these are fine. There's no right or wrong way. Depends what you want to do. I have forgotten right now how Fiji does it, but it probably just reflects the image, or it might do a 0. I think it actually does a 0 when I think about it. But what you can do is you can filter an image, and then you can zoom in on that edge in the output and see what it says. But it definitely doesn't make the image smaller, which is actually that's my preferred thing to do in Python. But hopefully on a large image, it's not a very large area, so you can almost just write off that part of your image and not worry about it too much. But you definitely have to think about it if you're working on very small samples of images, because you'll notice that the pixels around the edge can behave a bit weirdly in your output of your filter. So the reason I haven't gone into too much is because there's no right way of doing it. And
But the reason I'm asking for is if you have large images that are tiles,
Yeah.
one tends to store the raw data, but it does mean that if you want to do anything like that to a tiled image, you have to stitch before you filter.
Well, you mean filter before you tile, right? Or
Well, I mean not to filter because you lose the edges. So in order to tile correctly, you need to tile first in 3D.
it might still work though, because that's a small bit of corruption. And if you actually cropped out those few pixels, then you wouldn't lose anything. But I don't think it's a big deal. I think you could easily tile and then filter. I think that would be fine. And you could also filter before and then tile if you really wanted to make sure it was consistent. But yeah, generally it's such a small area, it's not such a big deal. Obviously you want to keep an eye open for it in case you start to see in your analysis something strange happening at the edges, or if you've done a filtering before the tiling, that it's not somehow creeping in. But yeah, generally you don't notice because it is just such a small part of your image. But it's good to raise your awareness of it. So that's an example of a nonlinear filter, the median filter. And I'm just going to take you through an example where filtering was actually very beneficial. So in this example here, we've got some cells stained with DAPI which are very close to one another. I've used a different lookup table here just to show you that they don't drop to 0 in between these cells. This is a wide field image, so there was out of focus light. So in terms of thresholding, this could be problematic. So this is a profile across the image, and you see that the separation of the cells isn't great. So it might be hard when we segment and try and split these to get separate cells. And that's exactly what we've done here. I've applied a threshold, and then I've tried to do watershed, and you see that it hasn't split these cells very well at all. So we want to try and use some filtering to see if we can get a better extraction of our signal that we're interested in. And what I've done is I've taken our input image and I've filtered it with a very high Gaussian, a very coarse Gaussian with a sigma of 80. And then what you get from this image is a very blurred representation, and this represents the low frequencies in this image. So if you squinted your eyes a lot, this is equivalent to a very strong Gaussian, and you can see that this is kind of the squinted version of this, right? And this is what we call like a low pass filter. So we've got rid of all the high frequencies. And then this is if we took our low pass filter and subtracted it from our input image, then we are left with our high frequencies, which in this case is just higher than whatever our low frequencies were. And so this is equivalent to a high pass filter. So we basically managed to split our image in terms of frequency using this Gaussian smoothing approach. Okay. So I should say, when we smoothed our image with this, we took a fresh copy of our input and then subtracted it from that to get this. Okay. And then if we took the filtered high frequency component and then did our segmentation, then you find that actually it's worked a lot better. We've got nice delineation of each of our cells. Okay. So that's just to show you a nice way of processing an image using filtering, which helped us extract the kind of signal that we're interested in. So actually, I mean, to say they're high frequency isn't really right. but they're the higher frequencies than this low frequency component that we managed to extract using this heavy Gaussian blurring. And because it was the lower frequencies that were disrupting the segmentation process, by extracting them using this, we managed to get a much cleaner result, which was useful to us. Okay, so that's actually the end of the filtering section.